Hello, everyone. Good evening to all of you who are watching from India, and good morning for people in other parts of the world. My name is Ashwini Dashgupta, and I am a faculty at Cheenta.com. Today, we have Dr. Sankhadip Chakraborty with us. Uh, Dr. Chakraborty is a researcher in dynamical systems. He initially did his bachelor's from Chennai Mathematical Institute and went on to do Ph.D. Um, in IMPA, Brazil. And then he is presently working as a postdoc at Southern University of Science and Technology in China. And it's pleasure having you, Shankodip. We can start with the talk. It's just to uh, preface one line about what our objective is. Of course, we would be presenting a topic. Dr. Chakraborty will be presenting a topic. And we are also inviting applications to the research group on dynamical systems, who will be starting on with a reading project initially, and then it might go on to solving problems, research problems in the coming days. So, if you are interested to join that research group, then this is the initial talk that should give you an idea about how this subject is, what this subject is all about, and then of course you can get into that research group and do some wonderful work with Dr. Chakraborty. So without further ado, let me just add the slide part. And Shankadeep, over to you.
Okay, so thanks for the welcome. This is something that I have been meaning to talk about for quite a long time. I really like this, as you can probably tell, because I do research in this. And also, this is something that I have known about since I was in high school. So even when I was in high school, I was thinking about doing research in chaos theory or dynamical systems. Okay. So today I will try to give you, let's say, a high school level exposition of what it is all about, because chaos is not just math. Chaos is a science. Chaos is a new science. There are aspects of it that we pure mathematicians study. Okay, so that's first point. It's a science which can be understand somewhat at the high school level, and it is not at all easy. Okay, so there will be a lot of things that I won't be able to explain well. I won't be able to like show you all the details because it's hard math. Okay, I want to make that clear from the very beginning. It's very hard math, but the objective of the talk today is to show you the basic ideas of chaos. Okay, those who will join the research project with me might get to see more of these ideas. Okay, now let's start with the first slide. Maybe some of you like Big Bang Theory. It's an American sitcom about a bunch of physicists, scientists. So it kind of gives you a glimpse into the world of these brilliant people. Okay, now the picture you see on the screen is a screenshot from one of the episodes. So Leonard, this guy in the suit, the guy in the red suit, his name is Leonard. He is going to give a talk, much like me right now, and he's very nervous. And his friends are telling him, "Do you are you nervous? Start with a joke. Don't worry. Start with a joke. Everyone will laugh, and it will be fine from then." Okay. Now he tells a joke. I will tell you the same joke because that joke is useful to me. Okay. The joke is a farmer has some chickens that do not lay any eggs. He asks a physicist for help. The physicist does some calculations and says, "I have a solution. I know how to help you, but my solution only works for spherical chicken in a vacuum." Okay, so why am I telling you this joke? Because it kind of gives you an idea about how science works, especially how physics works. So we make a lot of strange, we make a lot of strange simplifications, but somehow it all works, right? So when we do the calculations, when you make the assumptions, at least to me, it seems absurd. But at the end of the day, we make it work. Our science has been very successful. Science, like you can see, product percentage technology, some expectations, and expectations are. You have probably expression rocket science. Rocket science in popular lexicon, rocket science means something that's very hard. So have you ever wondered why rocket science is that hard? Because we can make submarines, we can make missiles, my voice is breaking. Just a minute to try something.
Now it's better. Now it's better. So Shongodip sir is presently in China. So there might be some occasional haziness on disruptions in the internet connectivity. But can all of you hear my voice clearly? Is my voice audible? Okay. So it appears that Shonkodip uh, is having a network disruption. Uh, let's wait for a couple of minutes. In the meantime, why don't I tell you something that is happening in the other research group at Chinta? It's on geometric group theory.
Oh,
Oh, we're back. Okay, we're back. Yes, Pankadip,
oh.
yes.
Apparently, I don't need a VPN to access StreamYard. So, okay,
Okay,
great.
okay.
Fine, let's continue. Are you sure it's all fine? Can I continue?
Yeah. It
Are
is
you sure
fine.
it's all fine?
Yeah, it is fine. It's all fine.
What was I saying?
Yeah, you were saying about why rocket science is so difficult.
Kind of forgot. Yeah, rocket science. So why is rocket science so hard? We make chips. Hello?
Yeah, Shankodip, I think your
I
audio
think
is breaking.
someone.
Yeah, I think your audio is breaking. That's all right. You can try to fix it maybe. In the meantime, to the people who are already in the audience, let me tell you a little bit about the other research group that we have at Chinta. It's on geometric group theory. There is a very close connection between topology and group theory. And we work on that. There are about 7 to 8 people in that particular research group. We recently came up with a very interesting translation project of a popular text in that particular field. We're also working on a problem called the embedding problem of a hyperbolic plane. So let me explain to you a little bit about that. In the meantime, while waiting for Shankodip, okay, Shankodip is back, I think. Is he back? Maybe not. Still can't hear him. So I'll continue with my story. So maybe you have heard about hyperbolic plane. Hyperbolic plane is a very curious world. if you take a straight line and take a point outside the straight line, in the Euclidean world, you can draw only one line parallel to this one through that point. Maybe some of you know the name of the axiom that is ensuring this in Euclidean world. It's called the Playfair's axiom, right? Oh, I see Shankadip's head moving smoothly, so I'm assuming that he is
Yeah.
back with video. Okay, so please, Shankadip, why rocket
Okay.
science is so hard? Please,
Yeah,
I
it's
hope I
because
will.
the
Yeah, yeah.
so rocket science is difficult because rockets explode, and rockets are
Uh,
expensive. So when one rocket explodes, you lose millions of dollars, and it's hard to make another one. And why does rocket explode? We rocket engine is like not so different from other engines we make, right? It's not the same as a car engine, of course, but it's not that different. Rocket engines explode, but car engines do not explode. Jet engines do not explode, but engines explode. Why? Because inside a rocket, the pressure and the temperature, these things are very high, and the fluids kind of fluid behaves in a very strange manner, and we do not know how to study that. We have no idea about that. So we cannot model a rocket engine well. That's why. So nowadays, how do we make rocket engine? We do some modeling, of course. Some modeling we try, and then we try stuff, and something eventually works. Okay, that's how we more or less make rocket engines. We make like 100, one works in the end. We keep tweaking till it works. Okay, and you can see some of you must have studied some fluids. So there is the concept of Newtonian fluid, there is the concept of laminar flow, and there is that law Pascal. I think it's called Pascal's law that relates velocity, pressure, all that. All that is at slow speeds. For example, when you open a tap, in the beginning the flow is nice and smooth. If you open a little more, there comes a time when all hell breaks loose. Right? You see that everything is going haywire. That's the point where chaos is setting in. And we have no idea what to do from there onwards. Okay. So that is why rocket engines are so hard to make, because we have no idea how to deal with fluids at that temperature and pressure. Okay. Now, of course, scientists are smart. They knew, they have known this all along. They always knew that chaos exists. We do not know how to deal with chaos. We know, like when the conditions are too extreme, there are too many variables. We do not know how to deal with that. Scientists always knew about that. But the science of chaos, the science of dynamical systems, is quite new. It only came up in the 70s. So why is it so new? It's because before the 70s, the scientists used to think that chaos happens because there are variables that we don't know. For example, the weather. The weather is a very complex system which has many, many inputs, many, many factors. We know very little about those factors, right? So scientists used to say that weather is unpredictable, weather is chaotic, because it has so many factors, so many random things. We do not know those factors. That's why we cannot model weather. We cannot predict weather. If theoretically we knew all the variables, all the factors, we could predict weather. So this is what scientists used to think before 70s. Now a revolution happened in the 70s. So I don't know if you have read the abstract of the talk. It says something about deterministic chaos. So there is random chaos that we have no control over, and there is deterministic chaos, which is where we know all the variables, we know all the equations, all the variables, we know everything. even then we do not know how to handle the situation. That is deterministic chaos. And that is the revolution that happened in the 70s. Now I'm going to tell you more about it. So there was a guy called Lorenz, Lorenz. I'm mentioning the spelling because there was another guy called Lorentz, Lorenz, some other guy. Okay, so this guy Lorenz, he was studying weather, and he was also a mathematician. He was a meteorologist come mathematician. So he had a habit of playing around with a computer. He used to take climate data. He used to make his own little models because remember this was 70s, so he had very little. So he had a very weak computer, very small, very weak. So he couldn't really model really complex systems. Okay, so he was playing around with his little computer, and he used to make some toy models of the weather. Okay, he like very simplified, just 3 4 factors, and he used to play around and see what happens. So one day he input some data, he got some results, and next time, instead of inputting new data, he input the data from the previous calculations into the machine again, just for fun. Okay, because like if he inputs the same data, the output should be the same, right?
Right.
Yeah, but that did not happen. He saw that the output he got in the first place and the output he got by feeding the data from the first iteration into the system again were wildly different. There was like nothing in common between the two sets of data. He thought, and remember, this was like the beginning of computation, I mean, beginning of personal computers. He thought, this is strange. This is probably like my computer is probably wrong. Something is like, it has probably broken down. He did the experiment again, got the same thing. He got better and bigger computers, again, same thing. Then he started thinking, okay, there's something fundamentally wrong about this. Then he understood that the data he was inputting in the system was rounded off because the machine was calculating the data till like 100 places and just printing till 2 places. Okay, so the data he was inputting is not exactly the data he was the which was the output from the previous one. Okay, but the difference was very small, and intuition tells you that if the difference is small, the difference in input is small, then the result should be similar. But that's not what happens. So this started the journey of deterministic chaos, which says that if you there are systems where even if you have a slight difference of initial conditions, then the resulting dynamics, resulting whatever you got, the results can be very different. Okay, this is the most commonly accepted definition of chaos: sensitive dependence on initial conditions. Okay, but the theory of dynamical systems obviously is not limited to this. It's very broad. There are many ideas, and we will start seeing those ideas. We will first of all we will try to understand what causes it, like what causes sensitive dependence on initial conditions. Actually, we don't really know. We know some of the mechanisms. As I told you in the beginning, chaos is really hard, okay, extremely difficult. So we know some of the mechanisms, but most of it is a complete mystery. Now, this much was story. Now I have to get a bit technical. Please forgive me for that. Now the math starts. Can you see my screen?
Yes, I can.
I mean, can you see my board?
The board, yes. I can see the board.
Oh, I cannot for some reason. What is a dynamical system? Anything that evolves with time. So those of you who have studied differential equations know what a flow is. Okay. For example, you suppose you have some dy dt equal to y square. The solution to this will be y equal to some function of t. That is a flow. That is something that depends on time. So this is called a continuous dynamical system. And there is another thing which is called a discrete dynamical system, which goes like this, which is a map from, say, some space to the same space, fx to x. So starting with some point, say x naught, you keep applying f. So fx naught, then f of x naught, then f of x naught. System, because you are like making jumps from x naught to you are going to fx naught, which is say time one. Then from fx naught you are going to f of x naught, which is seen as time two. Okay. So these are continuous and discrete dynamical systems. Just for the sake of completeness, I need to tell you that there are other dynamical systems, and I myself didn't know that until recently. So as I was preparing for this lecture, I was talking to my colleagues in my dynamics research groups, and I discovered that there are dynamical systems like nowadays, very recently. Now there are dynamical systems that do not have any notion of time. Okay, so the idea of dynamical systems has been generalized to the idea of group actions. So those of you who know some group theory might understand what I'm saying. So time can be seen as a group. So in the first continuous dynamical system, the time belongs to the real numbers, the set of real numbers, because you can consider any time, any value of t. In the second case, in discrete, time is say n, natural number. You can have time 1, 2, 3, 4, like that. And nowadays, in the modern definition of dynamical systems, time can be any group. Okay, and there is no present, there is no past. And I myself know very little about it, so I cannot help you with that. But I needed to mention this for the sake of completeness. Okay.
I should just
Anyway.
interject and say that I, in our language, we often in group theoretic language. I work in group
Hmm.
theory, so we sometimes talk about dynamical systems in the boundary of a certain space, of a topological space, and that is essentially a group action on a compact matrix, on a compact Hausdorff topological space. So, and there is a dynamics of the action. I mean, you can see points flowing from one point to another in that particular space under the group action.
But there is no present or future, right?
There is no present or future. The group is group.
Yeah.
The group can be really complex. I mean, it could be a fundamental group of some Riemannian manifold or something. It could be very interesting. Anyway, continuing, please.
So people are working on this, but I don't know anything about this. I need to find out. uh, okay. this is the definition of let's start with continuous dynamical systems, because that's what came first. Obviously, because physics is full of differential equations, right? For that reason, continuous dynamical systems came first. Now, if you if you solve something like, say, dx dt equal to some linear function, you do not get chaos, right? Because if the initial conditions are close, then the answers are going to be close as well. So if you make a little error in your measurement, it does not matter, because it kind of so it's a, even if you make a small error, the approximation is good. But when you have some nonlinear function, the analysis is really hard. And you must have some those of you who have studied some physics, you have surely seen things like that, especially when you have some partial differential equations. This is very common in physics. For example, if you have, say, fx comma y comma z, so it's a function of three variables, and you have a differential equation in terms of del f del x del f del y del f del z. For example, the Schrödinger equation in quantum mechanics, it's like that. And if you have solved equations like that, you know that unless this is separable, yeah, electrostatics, electrodynamics, you get these equations there as well. And you probably know that unless this equation is separable, the situation is pretty much hopeless. You cannot do anything about it. You are completely lost. Okay, so uh, we sometimes make the assumption. So when I learned about these things, I did not have a profound understanding of why this works. Now I understand. Okay, so we make an assumption. Let's see if there is separable solution. What does that mean? So let's see if this can be expressed in terms of f1x times f2y times f3z. Okay. So if the variables can be separated as a product, and when you make this assumption, sometimes what happens is you get some function of x plus some function of y plus some function of z identically equal to 0. And then you make the claim that these functions, these xyz variables, are independent, right? So this can be true if and only if fx equal to 0, gy equal to 0, hz equal to 0. So this can be true only if the functions are independently 0. And then you can solve this as a system of three one variable equations. Now, whenever you have linearity in a system, that system does not show chaos. Whenever you have non-linearity in a system, that system can show chaos. Why is that? It's because when a system is linear, it can be broken up into smaller systems. For example, I'll show you another thing. Two variable, second order linear differential equation, like y double dot plus, say, ay dot plus by is equal to 0. You must have seen this equation, right? This is standard in 11-12 syllabus. And how do you solve it? You say that as this is linear, the solution of two solutions is also a solution. The linear combination of any two solutions is also a solution. Then you make some assumption. You find some, yes, exactly, Swastik. You find some special solutions, and then you say that the general solution is a linear combination of the special solutions. So basically, the linearity is is allowing you to break the system up into easier systems. For nonlinear systems, doesn't happen, and that can create a lot of problems for you. Okay? So again, as this is one of the most important points in chaos theories, that's why I'm repeating this. Okay? Whenever you cannot have subsystems inside a system, that can be chaotic. Like everything is being mixed up. Okay, there are no small independent regions. Everything is being mixed up. Whenever that happens, you can have trouble. And this is the main idea of ergodic theory. Ergodic theory is something that you have seen in thermodynamics, kinetic theory of gases and stuff. So remember, there is something called the ergodic hypothesis, which says that the uh, time average of a particle inside a chamber. So you have gas in a chamber. The time average of a particle is the space average of all the particles. You must have seen this in kinetic theory of gases, and that works because we assume that the one particle whose time average we are taking is free to roam around the whole system. Okay, so the whole system is getting mixed up, and that's a difficult thing to deal with. Okay, so chaos is the idea of chaos is very related to the idea of non-separability of the system and the ergodic hypothesis. Right. Let's move ahead. Now, you have seen systems. I mean, differential equations in one dimension. Some of you must also have seen it in two dimensions. I will show you now. Something like this. Say dx dt is, say, ax plus dy, and dy dt is, say, cx plus dy. So this is sometimes also written as x dot y dot is a b c d, a matrix, times xy. Okay. And now you need to understand. Now you need to understand the idea of a vector field. I'm pretty sure, like, people who have done some physics know vector fields. I'm pretty sure about that, but I will tell you anyway. So it's nothing but a visualization of the system. What do you do? So the solution is going to be something like xt comma yt, right? So it's going to be a curve in R2. I will draw R2 here, x, y. The solution is going to be a curve. Interesting property of this curve. If you take at any point, at the point, say, let's say x naught, y naught, then the tangent vector at that point is, so, okay, do I need to do this rigorously? Fine, let me do it. It is ax naught plus y naught plus x naught, comma, cx naught plus dy naught plus y naught. Where did it go? These two on the right hand side, they are kind of arrows all over the distributed all over the plane. Okay, they are kind of arrows distributed all over the is a curve such that at each point, the arrow at that point is tangent to that curve. And this shouldn't be new to you, because you know that derivative is related to tangent of a curve, right? Derivative is related to tangents, and dx dt is the derivative of x, dy dt is the derivative of y. So clearly this arrow is kind of a generalization of that to two dimensions. So any such system can be represented as a bunch of arrows everywhere. Okay, that's the main idea. I hope this is more or less familiar to you, especially if you have seen this in physics. Okay, and by the way, these solution curves, they are called integral curves because you get them by integrating the vector field. Now, there is something called a singularity of a vector field. What does that mean? It's a point where the vector field is zero. So if you start from that point, then your derivative is zero. So you don't go anywhere. You just stay put. But how do the points behave around? How do the arrows behave around that point? They either come in from all sides, or they move. I mean, they move away from all sides, or some arrows come in, arrows move out. Okay? This is called a sink. This is called a source, and this thing is called a saddle. This tells you one thing. This tells you one thing, that the system can be understood in terms of the singularities. Why? Because all curves start from a saddle or a source and go to a sink. So suppose here's a source or a saddle, and here's a sink or a saddle. Saddle also works. Sink or a saddle. So all curves start from one fixed point and end at one fixed point. They don't really reach the fixed point, but they kind of tend to that fixed point. It's always like this. So given a vector field, if you understand the singularities, you understand the dynamics, you understand the system. This is very important, because if I change the vector field a little bit, going back to the equations, where was that? Remember, you are trying to understand. Remember that you are trying to understand the system in terms of the diagram, right? So, given this system, you look at the diagram, you see, okay, these are the vector fields. These are the sources. These are the sinks. Okay, I know what's happening. Okay, it's like that. Now, the question is, if I change these A, B, C, D parameters a little bit, does the vector field look the same? Does the dynamics change? If we perturb a little bit, A, B, C, D, if we change A, B, C, D a little bit, if the vector field more or less looks the same, like, oh, okay, it had three fixed points. This one also has three fixed points. One source, one sink. Okay, fine. One source, one sink. So if those things look more or less the same, then such a system is called structurally stable. Just so that you do not get confused, note that here we are talking about the whole system at once. So when we started, we were talking about sensitive dependence on initial conditions, right? There, the system was constant, but we were changing the like point a little bit. Here, I'm changing entire system and trying to see if the behavior is stable. So this is a different concept. Do not get them confused. Structural stability is the stability of the whole system, and chaos, the sensitive dependence of initial condition, that thing, that is the stability of one trajectory. Right. Now, structural stability was pretty much dead for a very long time. Nobody wanted to work on this because this was very hard. Then one day, now again, story, we're back to stories. There'll be like 5 minutes of stories. One day, a Brazilian mathematician called Mauricio Peixoto, I have had the pleasure to meet this guy. He's a legend. Mauricio Peixoto. He went to work with Lefschetz, who is another legendary mathematician from 19th century, I think. Very long ago, long ago. So he went to work with Lefschetz, and they worked together on structural stability of vector fields. And the result he found is called Peixoto's theorem, which is like a milestone in dynamical systems. And that says uh, the system says on a surface is, what is a surface? It's like a torus, a plane, or a sphere, stuff like that. Anything that has two dimensions, right? On a surface, a vector field is structurally stable if and only if it is what I just described. It has some fixed points. In fact, in this case, it's periodic points, not fixed points. Periodic points means like it comes back. Okay, so there are closed orbits like that. It it comes back. It has a finite number of periodic points, and like all orbits start from one and end on the other. Okay, if on a surface, if a vector field is like that, then it is structurally stable. So basically, it's a theorem that formalizes what I told you before. Okay. And by the way, there has to be like finitely many fixed points of periodic orbits. If you have infinitely many fixed points, then it all goes haywire. Okay. Now, this is a theorem for two dimensions for a surface. And when this theorem came out, many people started thinking that can this be generalized to higher dimensions? And one of them, particularly, one very famous guy, I also have had the good fortune to know him, Stephen Smale, who is famous even outside dynamical systems. He made very important contributions to like all over mathematics. So Stephen Smale, he was kind of certain that this can be generalized to three dimensions. But one guy, some other mathematician, he sent him an example of a three-dimensional dynamical system, which is structurally stable, but it has infinitely many periodic orbits. And first, he did not. Smale did not believe this guy. He said, "Hey, no, it's counterintuitive. It has to be false." He verified this for a very long time, and at that time, he was working with Mauricio Peixoto at the IMPA. So that's where I studied as well, at in Brazil, Rio de Janeiro. Rio de Janeiro. So they were both there, and Smale was trying to understand, hey, what's happening? What is going wrong? What's the problem? Eventually he understood what is the problem, because there are, in three dimensions, there are situations where infinitely many periodic points cannot be perturbed away. So you have a system which has infinitely many fixed points, and even if you change the system, perturb a system a little bit, you cannot get rid of those fixed points. They continue to exist. By the way, I want to make a little detour here because there is something that I wanted to tell you but I missed. Chaos cannot exist for unpredictability cannot exist for flows on dimension 1 or dimension 2, because if you have something on the real line, so say dx dt equal to something, then it's just like from one side to the other, that's all. Okay, or maybe sometimes it can also come back a little bit, but cannot get very complicated. If you have something on a on the plane and in a bounded region of the plane, then there is a theorem called Poincare-Brendixen, which says that the behavior you have a solution, some integral curve which is confined in a region, then that integral curve has either that integral curve either tends to a fixed point or it tends to a limit cycle. What is a limit cycle? It's a closed curve. So basically, there's a closed curve to which this converges like this. Okay, it approximates the closed curve. So the Poincare two-dimension systems, I mean, flows cannot get too wild. They either go to a fixed point or they tend to a limit cycle. That's it. Intuitively speaking, it means in two dimensions or one dimension, there is not enough space for the curve to get crazy. Okay. But in three dimension, you can have very complicated behavior even in limited space. So what happens in three dimension? Like you have space, right? You come like this, and you make a detour through the space, and you go inside, come outside, do all kinds of crazy stuff. Cannot do that in dimension two. Okay? But this is for flows. For discrete systems, you can even have chaos in dimension one. So in that sense, discrete systems are more complicated than continuous systems. Anyway, coming back to Smale, Smale was in Rio studying this counterexample in dimension three, which had infinitely many periodic points, and the periodic points could not be like perturbed away. Okay? And he toiled and he toiled and he toiled, and finally he understood what was causing the problem, and he produced a very simplified example to to explain this phenomenon. And I will tell you what that simplified phenomenon is. It's called Smale's horseshoe. Now, before I tell you like the before show you the actual construction of the horseshoe, I would like to tell you two things. I don't know if you have seen how bread is made. So bread when you make the dough for a bread, the bread is like the dough is elongated, it is cut in half, and one half is put on the top of the other. Again, they're elongated, cut, and one half is put on the top of the other. So what's happening? In one direction, there is an elongation taking place, and in the other direction, a squishing is taking place, and that mixes the dough well. Obviously, it does, because that's why the baker uses that technique, right? The baker wants to mix, the baker wants the dough to be homogeneous. That's why he does that process. This is one way to look at the horseshoe. The other way to look at the horseshoe is uh, initial initial sensitive dependence on initial conditions, right? So 2 points that start close have to diverge, like this. Now, if the map brings points together, if the map, I mean, if the flow contracts the space, that is not going to happen, right? Because if the space is contracted by the dynamics, then the points are like the trajectories are going to come closer. So chaos is not going to happen. So some going apart, some expanding phenomenon has to take place. Okay, that's where the elongation comes in. So expansion. But there is another problem. If you have only expansion, then it's not interesting dynamics, because like you start somewhere, all the trajectories escape to infinity. Like everyone goes their own way. That's not interesting. You want them to stay separate but also come back together, like get intertangled in a very complex way. So you're trying to produce chaos, you're trying to produce something very complex. So you need a way to like expand that whole thing, like break, I mean, cause trajectories to move away, and you need another mechanism to prevent them from going too far away. So they do not behave equally because of the expansion, and they do not diverge too much because of the contraction. That's what produces the intertwined behavior. Okay, this idea is called hyperbolicity. Hyperbolicity. Hyperbolicity is the idea of expanding one direction is and contracting the other direction. And this is the best understood mechanism of producing chaos. Chaos can be produced in many other ways, and we have no idea about them. Absolutely nothing. Chaos is harder. I keep saying this, but yeah. Anyway, so what does he do? So what did Smale do? He took something like this. Okay, I want to go to the next board. So it's a square with two semicircles attached to it. So what the map does is, it's a discrete dynamical system. Okay, so it's a map from, suppose this object is called C. So it's a map from C to C. What does it do? First, it elongates the thing. Then it contracts the thing, produces something like a strip like this. Then it folds the strip like this, and places it back inside the original thing. Like this. So this was C. The original thing was C, and this is FC. Smale proved that this thing, this dynamical system is hyperbolic, of course, because you can, like, you are squishing it and you are also elongating it at the same time. This is hyperbolic, and this has infinitely many periodic points that cannot be perturbed away. So that's why Peixoto's theorem does not hold in three dimensions or in higher dimensions. Okay? By the way, Peixoto recently passed away. He lived till like 97 or something. I saw him last year, and he looked perfectly normal at 97, better than most people at 50. Anyway, so FC, huh? What's happening? Just a moment. Let me get back to the correct slide. I would give you a bit of idea about how he did it, but I won't show you the entire calculation because it will take too much time. Um, so what he did is he note that this is not an invertible map, right? Because like what you are getting in the end is a subset of what you started with. Right? This is not an invertible map, but there is a subset of C restricted to which it is an invertible map. That's usually called lambda. And how is it obtained? It's just by studying. Okay, so you have this. If you do this once more, then you will see that inside those things, those two handles, there is a smaller structure. So this handle, obviously, it is this part. It is invariant if you apply the function once. Then you will find a finer thing inside if you do this thing twice. That is invariant under two iterations. If you do this over and over again, then eventually at the limit you will get a set that is invariant under the forward dynamics. And that's going to be kind of a Cantor set if you know what that is. Now, if you now do this backwards, then you will get another set which is invariant under the backward dynamics. And then you take the intersection of those two, and you get something which is invariant under forward and backward dynamics. And that's the whole thing. I'm sorry that like I'm not explaining this very well, because if I start doing that, it will take too much time and we will get off topic. You can find this on the internet easily. It's very common. I will just show you a nice picture. Here, this is the horseshoe. This is how it's happening. And that's the, you see, there is one vertical horseshoe and one horizontal horseshoe, and there is a very fine structure because you're doing the same thing over and over again. And there is a intersection between the two. That's the lambda, which is the invariant set. Anyway, yeah, so the last thing I wanted to talk about, actually, this was supposed to be the first thing, but I kind of got lost, is the Lorenz set, which is like one of the most famous images of chaos. You must have seen this before. This is called the Lorenz butterfly, I think. So, what did happen? Lorenz, coming back to Lorenz, remember he used to simplify the weather. He used to find some easy equations and he used to study them on his computer. Then what he did is he started making it easier and easier. He wanted to see how easy he can make without losing that complex behavior he was getting. Okay. So eventually, what he came up with was this set of equations, which describe the convection of air currents. And you probably know how that happens. So, air, when gets heated, it rises up, and as air in the upper atmosphere is cool, it again comes down. So it creates a cycle of air. So this is, in some sense, a model of that. Fortunately, it is a model of something else as well, which is nowadays known as Lorenz water wheel. And I will show you what that is. And that actually makes it much easier to demonstrate what these equations do. Okay, I will start a video. I need to share the screen. Give me a moment to get the video on screen sharing. Oh, there's an option to upload the video, but I think that might take too much time. Share screen. Let's share screen.
Just as Shankadip is trying to share the screen and everything, let me answer some of you are asking about openings in this particular research group. There are only 6 slots in a given research group usually. And to apply, you can just send your CV, your personal resume, to and why you want to be a part of this group to helpdesk@cheenta.com. You can send it by email, and we will respond. There are many applicants. We cannot respond everyone, and we cannot take in everyone. I'm sorry. We will respond to everyone, of course. And the output of this project initially will be the reading project itself will improve the understanding of the subject, of course, but eventually we would hope to um, go into some sort of a research problem and publication and so on. Okay, I think this is shared. The screen is shared. Yes. Shankari, we can see the screen. Yeah, you can.
Can you see it?
Yeah, I can see the
Can you see?
screen. Yes. Yes.
Yeah, you can see. Can you see two wheels?
Yes,
Okay,
I do.
so it is called the Lorenz water wheel. So what's happening? This is something that you can actually make at home. So it's not too easy to make, but it's not hard either. So it's kind of like roundabout, the one that the type you see at fairs, and uh, it has many water buckets alongside it. I mean, along the length, water buckets, and every water bucket is identical, and there's a hole at the bottom of each water bucket, and water can drip from that hole at a uniform velocity. Okay, and there's a tap at the vertically above the center of the wheel. Now, if you open the tap a little bit, what will happen is, like the bucket that is at the top, that will start filling up and draining at the same time. Okay, so the bucket will never get filled up enough to start a dynamics. It will remain at the same place. And if you increase the flow of the water, so by the way, while the experiment is running, the flow of the water is constant. So if the flow of water is greater than the flow at which the buckets are getting emptied, you are going to start seeing dynamics. Now, this is a very complicated dynamic. So, what happens is it, given the value of the parameters, value means like mainly the speed of the flow, and the starting angle. See, you can see two angles on the on. I mean, above the wheel, theta not equal to 1 degree and theta not equal to 2 degree. That's the initial angle at which the first bucket is with the vertical. And this is chaotic, as you will see in the video, that this small difference of 1 degree over time will produce very different dynamics. That's point number one. And point number two is you will also see some plots in the on the screen. What I need to explain to you what those plots mean. Those of you who have again seen some Newtonian mechanics, you remember in Newtonian mechanics when we plot a system, we plot the position and the velocity, both things, right? Because you cannot give a system just with the position; you need both. Here also, we are going to give the position of the center of mass, because see, the mass is changing, right? The mass of the system is changing. So we need to take the mass into account. So, and again, this is a two-dimensional. So the center of mass is constrained to move in a two-dimensional plane. So two of the variables are going to give the position of the center of mass of the system, and the last variable is going to give the velocity. But instead of taking the linear velocity, we are going to take the angular velocity. So the two variables are x, y, position of the center of mass, and omega. Omega is the speed at which uh, the the angular velocity of the wheel, which can be positive or negative depending on the direction. Okay. For that reason, you are going to get a three-dimensional phase plot of the system. Now, notice, pay attention to what's happening. So initially, they kind of look similar. Now they're becoming different. Okay.
So this red and the blue green thing are the center of masses.
No, that's what I was explaining. So
Oh,
that's the phase space. That's the phase space, which has the coordinates position of the center of mass and the angular velocity. Because remember, if we just plot the center of mass, that's a two-dimensional system. And Poincare-Bendixson theorem tells us that you cannot have chaos in two dimensions.
right. Oh,
Okay, so if you plot it just in two dimensions, then it's going to be kind of a projection of this, so you won't be able to see the actual complexity of the thing.
right. Fantastic. Thank you,
Okay, I
Shubham.
will add to the stream. And I
Yeah.
saw your question. I saw your question. I saw your question. I will answer it at the end again. I actually explained this at the very beginning of the lecture, that there is a difference between randomness in a system and deterministic chaos. Randomness is when we do not know the initial conditions, we do not know the factors, and deterministic chaos, what I study, is when you know everything, even then we don't know what to do. The three dimensions in the water wheel where like x and y, the position of the center of positions of the center of mass, and omega, which was the angular velocity vector. Okay.
Right.
Anyway, so let me show you some more photos. These are plots of the Lorenz system for different values of the parameters. And this is to be expected because the Lorentz system has some nice solutions as well, right? So if you like, if the flow is really slow, then it doesn't even move. It's just a point. If the flow has a certain speed, then it's like just one side, a certain speed and a certain angle. If the flow has a certain speed and some other angle, then it's just the other side. Then there comes a point when all hell breaks loose and you get this like the two thing. So what do they represent? One, I will again show you another slide. This, so these are two parts of the Lorentz attractor. What do they represent? One side is spinning in one direction, the other side is spinning in the other direction. And this, okay, this is the last part of the talk. We are getting to the last part of the talk. We cannot finish speaking about chaos without speaking about fractals, right? You must have, many of you, I'm sure you have seen the Mandelbrot set, some really nice designs. Those are the most famous images of chaos. So what is a fractal? A fractal is an object that has a fractional dimension. For in this example, the Lorentz attractor, this object you were seeing on the screen, it has dimension between 2 and 3. What does dimension between 2 and 3 mean? Sorry, not today. Today it's beyond our scope. Because so in order to talk about dimension between 2 and 3, you will have to like redefine dimension, and that's a lot of work. We're not going to get into that right now. And I use another word which is attractor. What is an attractor? An attractor is some region in the phase space which attracts all the trajectories, not all the trajectories, many of the trajectories to itself. For example, if you on two dimension on the plane, if you have a vector field which has only one fixed point, and that is a sink, that's going to bring all the orbits, like all the integral curves to itself, right? That's kind of an universal sink. That's an attractor, as a sink is an attractor. But not this is an like kind of an universal attractor. Doesn't matter when you start, you are going to go to that fixed point. But if you have two sinks, then they're going to compete among themselves, right? Some of the trajectories are going to come to one sink, and this other trajectories are going to go to the other sink. So sinks, attractors, kind of have a region of influence, which is called a trapping region. This is a fitting name, right? Because they're trapping trajectories. Now, this thing you are seeing on the screen is an attractor. No matter where you start, you are going to converge to this set, and it's an universal attractor. It attracts everything, and it is also called a strange attractor. Why is it strange? Because it is a fractal thing. Actually, as far as I remember, there is a like whole big book, huge book. I don't remember the name. That only studies this set, like how the set looks. One big book just for that. It is so complex. Okay, uh, so it's a strange attractor because it has fractional dimension. It has fractal structure, and also like its chaos is not that well understood. So as I told you, hyperbolicity is just one of the mechanisms for producing chaos. In fact, that's what we work with. It's IMPA was the pioneer in hyperbolicity. Because of Peixoto, Smale, and Palis, my advisor, Marcel Viana, all of them, they are the founders of the hyperbolicity theory. But there are many other many other mechanisms for producing chaos that we do not understand at all. So it's like wide open. Anyway, yeah, that's pretty much what I wanted to talk about. Any questions?
Thank you, Shankadip, for that talk. Since in the usual seminar hall, it would be a great point to thank you for that. But since I am the only one present here, I do it on behalf of the students. If you have a question, please put it in the chat. You can put the question in the chat and we will be able to respond. And for others, this is just an announcement. The content of the reading project, we can share the PDF with you, Mr. Parisha, and it will have
Sure.
the details. The
So,
like,
just one more, Mandeep. Mandeep. So there are many, as I told you, chaos is a science. It's not just math. So there are many ways to get started in that, depending on how prepared you are. Okay. So I'm not decided yet how I'm going to start. So depending on the people I get, depending on the students I get, I could start from that book that someone mentioned, that Strogatz. Someone mentioned the book in the chat I saw.
yeah, yeah, yeah.
I can start from that, and if I get people who are like really have a really good background in mathematics, geometry, and etc. Because dynamical systems requires a lot of tools. You need to know geometry, topology, ergodic theory, algebra, many analysis, many things. So if I get students who have a like really sound background, then I'm going to start hyperbolicity theory directly, or maybe one-dimensional dynamics, because that's something I do not know well. So if I study it with you, it would be good for me as well.
Okay, I think that answers the question.
Any
You
more
can
questions?
always send, yeah, you can send your applications to. Yeah, this one was the name of the book, right? You can send your applications to helpdesk@chinta.com if you want. And I think there is no other question at the time. If you have more questions, feel free to reach us out. Oh, there is a question regarding full waiver of the tuition. So it's only available for the people who are teaching at Chinta. Some of the faculty members attend the research groups as well. So if you are faculty at Chinta, then there will be a tuition waiver available. Otherwise, there is no tuition waiver available. Okay, so that's that question. And if you have more questions, feel free to let us know, and we will be very happy to respond to those questions. And keep on enjoying research. It's great to discover new things and at least know about new stuff, the bleeding edge of mathematical science that is out there in the world. And we hope to come back to you with more of these things. Prerequisites in topology. Is your question about prerequisites in topology or for topology? If Shankodip, what is the prerequisite for knowing for dynamical systems as far as topology is concerned? I think you are muted. I cannot hear you. I cannot hear you. That's the problem. And if your question is about, no, no, still can't hear you. So if someone is asking for the prerequisites of knowing topology, like topology itself, I cannot talk about dynamical systems. Shankadeep will be back with his audio, I guess, and he will be able to do that. But for topology itself, high school level mathematics is sufficient. even set theory and some sense about how to add things, subtract things, addition, subtraction, multiplication. You don't even need division, I guess. You need division a little bit to understand some of the questions here. So to get started with point set topology, that's what you need. Um, and if you need to do something more complicated like algebraic topology or geometric group theory, something like that, then you need some more stuff. Like you need to know group theory. You need to know if you want to do differential geometry, differential topologies, for example. You need to know something more. I want to pursue PhD. Can I apply for this research track? Yes, of course you can, Saurav. One of the reasons people apply for research tracks at Cheenta is because they want to pursue PhD at a great university or something. And these research experiences are very valuable in the application process. So that's one of the reasons people. So in order to apply, again, I'm mentioning this over and over again. You have to send an email with your CV to helpdesk@cheenta.com, and we will be able to respond. How to become a TA and faculty at Cheenta? Okay, we do not have any vacancies at the moment, but you can always send your CV to helpdesk@cheenta.com, and if something opens up, we will let you know. Of course, you can also attend an internal training that happens for the prospective faculty members, so that next time we need someone, we hire from that. Okay, so that's the next thing. I will add Shankodip to the stream. Shankodip, are you audible? Maybe not. So I think there is some issue um, with the audio in Dr. Chakraborty's computer, so we can't hear him. There are only two active research tracks in Chinta. One of them is in dynamical systems, led by Dr. Chakraborty, and one of them is on geometric group theory, led by me. There is another one which might be coming up pretty soon. It's on automata theory, so and deep learning and stuff like that. Geometric deep learning, maybe. We will let you know if something comes up like that. Okay. Okay. I still can't hear you, Shankodip. Can't hear your voice. Something is happening. What I'm going to do is I will thank Dr. Chakraborty one more time and stop out here today. It was a great story that he shared with us. It's a rich field in research. I truly encourage you to pursue this and learn something exciting from him and on your way into this research field. Okay. Thank you, everyone. Thank you, Shankodip, for joining us. And good night to all of you. Take care. Bye.